So let's actually transition over into using PyTorch, and I'll show you how you can solve this classical linear regression problem using the gradient descent algorithm, which is used to train neural networks. So essentially, we're going to transition here from regular data science into some aspects of machine learning and deep learning. So here's what I'm going to do. I'm going to start introducing some of these features of the PyTorch Autograd library. And to do that, I'll create a model parameter. So why do we have this model parameter? The problem that I want to solve is essentially estimating the slope of this red line, okay? And the way that I'm going to estimate it is by using the data, using these blue dots, okay? So I'm going to feed in the blue dots into my linear regression solver, right, or estimator, which is going to use gradient descent. And I'm going to try to recover the shape of the strand between the values, the uppercase X and the Y. So ideally, I should be able to recover this value of the slope of the strand line that you're looking at. And the way that we're going to do this is a traditional way that we use in machine learning, which is to build a model. And our model in this case is going to be super simple, just one single parameter. We're going to call it W. And I'm going to initialize it using what's known as a torch empty method. I'm just going to say, hey, give me a single scalar. So here, this is the size. And if you take a look at the resulting tensor, it's a scalar. Now, if you call pt.empty, right, it gives you some value, some initialized value. In this case, we got lucky. It's pretty close to a 0. But I want to be more certain. So what I'd like to do is actually take this W and initialize it using a random value. And for that, I'll use pt. Actually, let's use this initialization function called uniform. So if you've ever seen this flat uniform distribution from -1 to 1, that's exactly what I'm using. So let me parse this out. This means go ahead and use the uniform distribution from -1 to 1 to initialize the value of the model parameter W and shove the result into W. Actually, let's do it this way. Make things easier. There we go. So now it will complain about the deprecation because I'm using an older uniform initialization. But now you can see that the value that we initialized the model to is this random value from the range of -1 to 1. And if you're wondering about the pseudo-random values, basically means that any value in this range is equally likely. That's what having a uniform distribution means. Okay, so that's W. And if you're wondering, if you're more of an expert in deep learning, you're wondering why I'm not using better initialization like Xavier or K-means initialization, it's because this is just a single parameter. I just don't have any additional inputs or outputs for this parameter to use more complex initializations. Now, the whole point of having this W value is that now I can actually use this to help me make guesses based on the data. So what does it mean to make guesses? Well, in machine learning, we have this concept of a forward function, which makes guesses about the data using the model. So our model is super simple. So let's go ahead and explain how we're going to make guesses about what is the predicted value of Y. So we're going to say that this model is going to generate predictions of Y simply by taking X and multiplying them by W. And then we'll return the predictions. This is all that this model is going to do. So we take the input data. Remember, these are horizontal axis values along the x-axis. Multiply them by a single model parameter that generates some predictions, and then we return those predictions. So just if you wanted to see what the example would look like, it would be forward of X, then W, and here are predictions. Well, obviously these predictions are terrible, right? If you think about the original values that we generated here, you can actually see them. For example, the first value for Y, what we say is the right value. It's -8. It's way off the prediction. But that's the whole idea behind machine learning, right? We have a way to model data, we make an initial guess, and then we improve that guess over time. So that's the approach that we're going to take here. So let's go ahead and do that. And then the question is, how do we estimate how well we're doing with guessing? Well, in order to do that, we need to be able to define what's known as a loss function, or if you prefer, cost function. So let's call it MSC for mean squared error. And this is going to measure how well we're predicting. And the way that it's going to measure is that first it'll estimate the error. And the error is simply going to be the difference between the predicted and the actual values. And then what we're going to return is the mean of the squared differences, so mean errors. So let's go ahead and return pt.mean error squared, right? So that's exponentiation in Python, and we're returning the mean squared. So this means that we can actually do things like MSC, take the actual values, right, from our data set, and then compare that to the predictions of the model based on the input data and the model that we're using, and return our error. And that's it. So this is actually the mean squared error based on the current versions of the model. Okay, so that's where we are. Now let's actually go ahead and start using gradient descent. So everything that you've seen so far is just basic definition from machine learning. There are different ways of solving this problem. How do you actually minimize loss, right? How do you reduce the loss of this function by changing W? There are different techniques for solving that. But the technique that we're going to use is gradient descent, because it makes use of the PyTorch Autodiff feature. And it's a very fundamental algorithm that you need to know if you ever want to get into neural networks. Now, in my implementation of gradient descent, I'm going to use this definition of epochs and learning rate. So these are constants. So if you're wondering how I got them, the answer is, the simple answer is trial and error. The more sophisticated answer is hyperparameter tuning. So if you're interested, happy to talk later about hyperparameter tuning. But for the time being, let's just say that these constants can be used to solve the problem. But what we really care about is solving the problem, not necessarily these constants. So the way that gradient descent is going to work is that we take a bunch of gradient descent steps. So what does this mean? Let's actually do, arrange epochs. Let's do these epochs of gradient descent. And here epoch means that we are actually iterating for the entire data set, training data set, to improve our model, to create our model. All right, so let's go ahead and implement it. The first thing that we need to do is figure out our predictions and measure the loss on those predictions. So what are our predictions? We're going to call them ypred. And remember that we do a forward method. We take x, w is our model, right? A simple model with just one parameter. So these are our predictions. And our loss is what we define using mean squared error as the difference between the actual values and the predictions. So that's it, right? So that's our loss. Nothing too complex so far. What makes this different is that notice that now we're actually doing this repeatedly. In the past, I showed you that you can compute these guesses, right? Guesses for y or predictions for y, just one at a time. But what we're going to do now is do these in epochs, right? In these complete passes over the data set. So in order to do that in context of gradient descent, here you need to start using something that actually has to do with the PyTorch Autodiff library. The first thing that you need to do is make sure that W is actually initialized with gradients. So this is the first kind of feature that I need to add here, which you may say feels a little bit magical. So let me go ahead and change this in the code, and then I'll explain what happens. Notice that now, when I'm creating this tensor, let me go ahead and reinitialize it. It has this feature that says requires grad equals true. Now, I'm going to give you an introduction answer as to why I'm doing this, and then I'll do a deeper dive behind Autodiff and actually explain in code how you can actually implement this grad on your own. At a very, very high level, what this means is that if you have a tensor, like in this case, it's a simple rank 0 a scalar tensor, requires grad equals true, ensures that you can actually compute gradients or derivatives in this case for the values of this tensor. So if you're not sure about the difference between derivatives and gradients, I'm sure you know about derivatives from college, but gradients, think of gradients as multi-dimensional derivatives. So if you compute derivatives across more than one variable, that's basically called a gradient. So this means that we can compute gradients for this value of the tensor. So if you're feeling unsatisfied from this explanation, don't be surprised, because the first time I saw that, I wasn't very happy with that explanation either. This is what this session is all about, teaching you what does this actually mean and how do you actually take advantage of this. Okay, so that's the first change that we've made, right? We redefined W to actually have this gradient feature. So what this means is that now that you have this gradient feature, the first thing you need to do is what's known as zero out this gradient. Now, this is the step that actually seems most magical to users of PyTorch. And probably one of the most frequent questions that I get is this zeroing out of the gradients. Do I need to do this here? Can I put the zeroing out of the gradients here? Can it happen after backward or before backward? The short answer is hang on. We'll dive a little bit deeper to explain what this gradient thing is. Why do you need to zero it out? And then you'll be able to figure out on your own where exactly it needs to happen in the implementation of your gradient descent. Now, the second step, which is loss.backward, at a very high level, again, this introductory answer, this is actually doing backpropagation of mean squared error back to this parameter, back to the model parameter. So it's figuring out how to change what is the gradient of W with respect to the loss. Or in other words, how do the changes of the W parameter impact the changes in the loss? Because remember, the idea is to minimize this loss. Minimizing the loss means improving the predictions that you're making with this very, very simple model. So these are your predictions. This computes the loss, the difference between the predictions and the actual values. And the idea is to improve on the loss. So how do you do that? If you've done gradient descent before today, you know that the approach is to take your model parameter and you can actually change the data, in other words, that value in the tensor, and reduce it by the learning rate times w.grad. So that's all. And in fact, if I go in and run this, assuming I didn't make any bugs while I was shedding, yeah, so you can see that this worked, right? So it ran for 100 epochs, which means 100 passes for this entire data set of 50 points. And then at every step, it was actually changing the original value of the tensor. Remember, we started out with the value that was about 0.8, and now it's basically 2. Right, that's the value that we use to generate the data set. So if this feels a little bit magical to you, I encourage you to go to Machine Learning 101, or if you're interested in the appendix of my book, I do an explanation of the intuition behind gradient descent. But conceptually, this should make sense, right? We're making guesses about W. We're figuring out how would changing W improve your predictions, or in other words, minimize loss. And we're changing W value in the direction to improve the prediction. So the w.grad is basically the kind of a change that you can make to W to improve the predictions. And if you've ever done linear algebra, you may have seen this kind of a solution, which is the analytical solution to linear regression. In fact, in PyTorch, of course, what you can do is figure this out on your own. So x.t is basically the linear algebra of operation of matrix transpose. So if I do this, it's essentially this left part in the parentheses. And then I need to raise that to the negative first power. So let's do inversion of this stuff. So here's what I get if I compute this first part of the analytical solution to the linear regression problem. And then I also need to multiply that by x transpose matrix multiply y. So that's the right-hand side of this problem. And now what I can do is multiply them together. Now notice that in this case, I'm dealing with scalars. So these are not matrices anymore. So I cannot use matrix multiplication, which is the @ sign to multiply these two. I have to use just a regular multiplication. But basically, if I apply this ordinary least squares solution to the original problem, right? Remember, we started out with this data set. Our data set of x's and y's is represented by these blue dots. And the idea was to recover the trend between them, sort of the statistics 101, right? Linear regression. And we've just done this two ways. One way using gradient descent, another way using this analytical solution. And in both cases, the result is the same, meaning that we can basically recover that underlying pattern in the data. If you're wondering, like, why am I going crazy with gradient descent? Why do I need all these iterations? The short answer is that if you look at the analytical solution, this is actually relying on a very computationally expensive operation known as matrix inversion. So if you have a data set that has a huge number of features, so think on the order of tens of millions, billions of features, this matrix inversion is big O n 2.3, so somewhere in that range. A naive solution would be actually big O n cubed, so it's not feasible for large data sets. But the nice thing about gradient descent is that it's scalable. You can actually scale it to many features. You can scale it actually across many nodes in a computing cluster. And although it gives you an approximate answer, gradient descent works quite well for modern neural networks. So the bottom line is that both solutions did not exactly recover that value of 2. Remember, we said that we'll take x and multiply it by 2 as the slope and then add some noise. Well, if you're wondering why this solution, even the analytical solution, did not return the value of 2, well, it's because that noise did not allow us to estimate the exact slope. We found an approximation, but that's the same thing that what the gradient descent approach gave us, right? Same idea. We're looking for estimate, for approximation. And in real data sets, you're going to have noise anyway. So running this computationally expensive, ordinary least squares approach is not really getting you a lot of benefit. So let's recap where we are. So we started out with a data set. Then we took that data set and ran it through this gradient descent algorithm for 100 epochs. Remember, 100 iterations or gradient descent, using the entire data set in this iteration. And basically at every iteration, we take our model, we make a guess about the whatever we're trying to predict, which is our y. Using that model, we figure out how good the guess is compared to the actual values. And then we do these, like, quote unquote magical operations. We zero out the gradient, we compute the backward loss. So I think everything except these question mark lines of code, everything except 6 and 7 should sort of make sense. And I think line number 9 will make more sense after this next part of the presentation. So what we're going to do is actually dive deeper into what does it actually mean to zero out the gradients? Why do you need that? What do you actually do when you backpropagate gradients? What does it mean? How does this change our model?